Hello everybody and welcome to Algo Expert. In this video, I'll be covering the question of compare leaf traversal. Now before we dive in, let's make sure we understand what the question's asking of us and the input and output structure. So for this question, we'll be given two inputs. The first input will be called tree 1, and this will be the root node of a binary tree. The second input will be tree 2, and this again will be a root node of another binary tree. Now what we're being asked to do is compare the leaf traversals of these two binary trees and determine if they are the same or not. So if the leaf traversals of these trees are the same, our function should return true, otherwise it should return false. Now the leaf traversal of a binary tree is simply the traversal of all of the binary tree's leaves from left to right. So if we're looking at tree 1 here, its leaf traversal is 4, 7, 8, 9. Sorry, not 9, 6 in that order. And if we're looking at tree 2, its leaf traversal is 4, 7, 8, 6 in that order. So clearly, looking at these two inputs, we can see they do have the same leaf traversal. So for this sample input, our function would return true. Now, a few notes here. A leaf is simply a node in a binary tree that has no children, so no left or right child. The binary trees that are given to us will have at least one node in them, so we will always have a minimum one node. We will never be given none/null, and all of our binary tree nodes have a left, right, and value attribute. The value is what you're actually seeing here, so 1, 2, 3, so on and so forth. This value will always be an integer, and all of the values in our binary tree will be unique. So in tree 1, it will have completely unique values, and in tree 2, same thing, it will have unique values, but they will not be unique between the two trees. What I mean by that is obviously we have a node 1 here and a node 1 here, so that's fine. That still means that within this tree, these values are unique, and within this tree, these values are unique. So that is really all I need to cover for this question. Now let's talk about how we can solve it. So as we start getting into the solution to this problem, the first thing I'm going to do is introduce us to kind of the brute force or naive way of solving this, and then I'll get into two more elegant solutions so you can see why these are better than the solution I show you right now. So the brute force approach, or kind of naive way to solve this, is to simply iterate through both of these trees one at a time in a pre-ordered traversal. Now, in case you forgot, a pre-ordered traversal means that we visit the current node, we traverse the left node, and then we traverse the right node. Now, when I say visit, this really just means process this node, so do something with it. And in our case here, visiting a node is just going to be checking if this node is a leaf node. And to check if a node is a leaf node, we just have to see if it has any children. This is a constant time operation. It's very easy to do this. So when we traverse this tree in the pre-ordered traversal, what we want to do is keep track of all of the leaf nodes that we see and in which order that we see them. So intuitively, we could create some type of array, and this array could just store the value of leaf nodes. So what we would do is we would start at node 1. We would kind of visit or process this node. We would say, okay, is this node a leaf? This node is not a leaf, and so what we would do then is traverse the left and the right subtree. Now we would start with the left because this is the pre-ordered traversal, and from here we would kind of process this node. Is this node a leaf node? It's not, and so what we would do is traverse the left subtree. We look at the left subtree, this node is a leaf node, and so we just add its value into this array. Now we try to process the left and right child of this node. Well, this is a leaf node, so it doesn't have any of those. So that means we go back up to this node and then we look at its right child. So now we're at its right child. From here, we check if this is a leaf node. It's not, so we go to 7 here to the left. We see this is a leaf node, so we add it in. We then come back here, we go to the right. We see this is a leaf node, and so we add 8. Then from 8, we go back to 5. Well, 5 is done. From 5, we go back to 2. 2 is done. From 2, we go back to 1. 1 is not done because we've only traversed the left subtree. So now we look at the right. This node is not a leaf node, so we try to go to the left. There's nothing to the left, so we come back up here, and then we go to the right. Right is a leaf node, so we add it in. Then from here, this has no nodes to consider anymore, so we go back to 3. 3 is now done. We go back to 1. 1 is now done. We have found all of the leaf nodes and the order in which we traverse them: 4, 7, 8, 6. So the point of this is to show you that we can actually find the leaf nodes by performing a pre-ordered traversal. And in this case, it's pretty simple to keep track of the order in which we visit them. We just store them in an array. So now we would do the exact same thing for tree 2. We would run the pre-ordered traversal. I'm not actually going to do it. And then we would create our array. So when we create this array, we're going to see again 4, 7, 8, and 6. We would then go through these two arrays, compare them together, and see if they have the same values. Now, if they have the same values, we will return true. If they did not have the same values, we would return false. And when I say same values, I mean same values in same order. So this solution is fine. It actually doesn't run in that poor of a time complexity. The time complexity here is going to be big O of n plus m, where n is the number of nodes in this tree, and m is the number of nodes in this tree. And then our space complexity is fairly complicated, but it's actually going to be big O of n plus 1 over 2 plus m plus 1 over 2. And I'll go through why we get that, but we can kind of get rid of the constants here. So the division by 2 we don't care about, so we would remove that. And then we have the plus 1, we don't care about that. And so our space complexity, theoretically in big O notation, will be big O of n plus m. Now, the reason why technically our more accurate way of saying the space complexity is n plus 1 over 2 plus m plus 1 over 2 is because the maximum number of nodes that we can have as leaf nodes in a binary tree is equal to this formula right here. Now, the reason this formula actually works is because when you have a binary tree, let's say we have a binary tree of some height h, the maximum number of nodes that could possibly be in this binary tree is going to be 2 to the exponent h minus 1. And if you actually had this number of nodes in a binary tree of any specific height, this would be what is known as a complete binary tree. So let's say we have a binary tree of height 3. So that's 2 to the exponent 3 minus 1. So that would be 8 minus 1. We could have a total of 7 nodes. However, the last layer of our binary tree could have at most 4 nodes in it if this was a proper and complete binary tree. So if we have 2 to the exponent 3 minus 1, that's the max number of nodes we can have in a binary tree of height 3. Let me just draw this out. We have a node here. So 1, 2, 3, 4, 5, 6, 7. We have 7 nodes in this binary tree, and you can see the last layer of this binary tree has more nodes, specifically 1 more node than all of the nodes contained before it on the upper layers of the binary tree. And so that's kind of why we get this n plus 1 over 2 for the maximum amount that we could have in this bottom layer, meaning the maximum number of leaf nodes we possibly have, because you do have the most amount of leaf nodes when you have a complete binary tree and you have a complete layer of nodes that have no children. So hopefully that kind of makes sense, but if you just look at what the worst case for your binary tree input could be, which in our situation for the space complexity would be a complete binary tree, you see the maximum number of nodes you can have as leaf nodes is n plus 1 over 2. And then of course we have to add m plus 1 over 2 because we have 2 binary trees that both are going to have arrays that store the order in which we visit those leaf nodes. So anyways, that's why we get that space complexity. But the point of me showing you all of this is that this is a bad space complexity. We can actually do this in big O of h1 plus h2 space, where h1 is the height of the first binary tree and h2 is the height of the second binary tree, which will be much, much, much better than the other time complexity we had of n plus m. Anyways, let me show you now the first kind of approach that we'll actually dive into in depth. This approach, as I said, is going to solve this problem in the same time complexity of n plus m, but now in an optimized space complexity of h1 plus h2. So the first thing to realize as we dive here into this first kind of official solution is that it's unnecessary to store the value of the nodes in which we visit in the pre-order traversal. We don't need to store the leaf nodes to be able to check if the leaf traversal is the same. And that is how we're going to get a better space complexity here of big O of h1 plus h2, because we're not going to be using an external data structure like an array to store all of the leaves that we find, which can be quite expensive in terms of the amount of space we use on very large binary trees. Instead, what we're going to do is the exact same thing previously. We're going to run a pre-order traversal on both of these trees, except during these pre-order traversals, we're going to be looking for the next leaf node. So as soon as we find the next leaf node in both tree 1 and tree 2, when I say next leaf node, I'm talking about the next one to be visited that we have not already visited in the pre-order traversal, we're going to compare these leaf nodes together and check if they are the same. So in tree 1, we're going to do our pre-order traversal, so we'll go from 1 to 2 to 4, we find that node. In tree 2, we'll do the pre-order traversal, so from 1 to 2 to 4, we'll be running these kind of back to back, and then as soon as we find the next leaf node in both of these traversals, we're kind of going to pause, and we're going to check if these leaf nodes are the same. If these leaf nodes are the same, then in this example here, we know that the first node in the leaf traversal of both of these trees is the same, so we keep going and we look for the next leaf node. So now we know the first one is the same, so we're all good with that, but we need to find the second one. So the second leaf node involves us going to 5 and then to 7. So we find 7 in tree 1. And from tree 2, all we had to do is go from node 2 to node 7 in the pre-order traversal. So now we find the next leaf node in both of these trees. We compare their values. If they're the same, we move on and we look for the rest of the leaf nodes. So they are the same here, so we would keep going. So from 5, we can find the next leaf node by just going to its right child, which is 8. But from tree 2, we need to go all the way back up to 1, then to 3, then to 5, and then to 8. So now we find the next leaf node in both of these trees. We kind of pause the pre-order traversal. We check if these leaf nodes are the same. If they are, we look for the next leaf node. And then we keep going until eventually there's no more leaf nodes in both of these trees, or we've processed all of the leaf nodes and made sure that they're all the same. So what this effectively will do for us is the exact same thing as the previous solution, except now we're kind of checking one step at a time. So as soon as we find a leaf node in both of the trees, if they are the same, rather than traversing one tree in its entirety, storing all of the leaf nodes that we find, then traversing another tree, storing all of the leaf nodes that we find, and then comparing the leaf nodes. In this solution, we're comparing the leaf nodes as we find them and trying to find them kind of at the same time, right? So I'll show you now in more detail exactly how this works, but that's really the idea behind solution 1. And what that allows us to do is actually run the solution in big O of h1 plus h2 time, because there's no extra storage in the form of an array that we need to use. Instead, all of our space is coming from our recursive call stack if we decide to implement this recursively, or from a regular stack, which we'll use to implement the pre-order traversal iteratively. So let me just move kind of both of these inputs over a little bit and make them a bit smaller, just so I have some room here to actually write out a few stacks that we'll need to use. So what I'm going to do now is run us through more formally exactly how this will work. So the idea is we're going to perform a pre-order traversal on both trees at the same time. So to perform a pre-order traversal iteratively, which we're going to do here because it will just lead to a simpler implementation, is we need 2 stacks. We need a stack that's going to store the nodes that we're currently processing for tree 1 and for tree 2. Now this will effectively do the exact same thing that a recursive pre-order traversal will do. It's just going to do it without all of the recursive calls. So the way that we kind of start this traversal is we add both of the root nodes onto their respective stacks. And actually I'm going to write it kind of at the bottom here, just so I have room to add things above them. But the point here is that the top of the stack is kind of up here. So top of the stack is here. Okay, so now that we have these stacks, what we're going to do is kind of set up a while loop. And I'll write a little bit of pseudocode here just because it will make it a bit clearer. So we're going to say while, and then I'm not going to write out the condition. I'll kind of just say what it is. The condition is while this stack and this stack both have elements in it. So while there's nodes to visit in both of these stacks or both of these trees still in the pre-order traversal, then we'll keep looping here. And anyways, inside of here, what we're going to do is we're going to look for the next leaf for tree 1. And then we're going to look for the next leaf for tree 2. These are the 2 pieces of information that we want to find. So we're going to say that next leaf 1 is equal to, and then some function that will take this stack here and find for us the next leaf node in the tree, starting at this node for the pre-order traversal. So what we'll do is we will call some function. This function takes in these stacks, and then it starts kind of performing the pre-order traversal. And then as soon as we find a leaf node, we'll return that leaf node to both of these kind of variables here, and then we'll use these values to check if these leaf nodes are the same. Okay, so next leaf 1 and next leaf 2. Next leaf 1 will start by looking for the next leaf in tree 1. And so what that means is we look at this stack right here. We see we have node 1 on the top of the stack. And so we pop this off to indicate that, hey, this is the current node that we're looking at. I'll kind of circle it over here. And we're going to check if this node is a leaf node. If this node was a leaf node, we would just immediately return it. The reason for immediately returning it is because this is the next leaf node, right, in our pre-order traversal. Anyways, in this case, it's not. And so what that means is we need to check if we have a right child and check if we have a left child. And if we do, we need to add both of these onto our pre-order traversal stack. So what we'll do is we will add node 3, the right child on the stack first, and then we will add node 2, the left child on the stack second. The reason for doing this is because we want to make sure we add the node to the right first so that it is processed after the node to the left. So I could say this in the other way around too. We want to make sure we add the node to the left second so it's popped off the stack before the node that we inputted that was to the right. So hopefully that makes sense. But since the stack follows the last in, first out principle, if we want to have a pre-order traversal, we have to push the right node first and then the left node, because that means now the left node's on the top of the stack. So it's the next one to be processed. So now what we do is we keep looking for the next leaf node, right? Because we looked at this node, it wasn't the leaf node. So then we added its left and its right child to see if those were leaf nodes. And now we need to process these left and right children. And so we pop this node off, and now this is our next kind of current node. So I'm going to add this node as our current node just by circling it. Now from this node, we check if this is a leaf node. It's not a leaf node, and so what that means is we need to process its left and its right child and add those to the stack to see if those are leaf nodes. So we take the left child, we take the right child, we push the right child onto the stack first, so 5, and then the left child on, which is 4. Then we pop node 4 off of the top of the stack because this is the next node that we need to process. So now we're currently on node 4. Node 4 is a leaf node, and so what we do is we just immediately return node 4. So node 4 now gets returned over here to be the next leaf 1, because this is the first leaf node that we found, or the next leaf node in this pre-order traversal. So let me just kind of write a 4 over here. So that's equal to 4 right now. Now we go over to tree 2, and now we do the exact same thing, except we're looking for the leaf node in tree 2. So we're on node 1, so we pop this guy off. We say this is our current node. Is it a leaf node? No, it's not. So we push the right child on and then the left child on, so they're processed next. So we push right and then left. Okay, so now we pop off node 2 because this is the next node to be processed. So now node 2 comes off. This is the current node. All right, is node 2 a leaf? No, it's not. It has some children, so we add both of those children on. We're going to add 7 first, the right child, and then we add 4, which is the left child. Okay, so now we pop 4 off of the stack. We see that 4 is actually a leaf node, so we consider it. And since it's a leaf node, we immediately return it to next leaf 2. All right, so now we see that both of these leaf nodes are the same, which means the first leaf node in the leaf traversal of both of these trees is the same. That is good. We can continue looking at the rest of the leaf nodes. So we kind of erase this now. And now what we do is we call to look for the next leaf node again. So we keep going because there's still nodes in here. So there's still leaf nodes that we need to consider. And we just keep running this while loop. So now we do another iteration. And now next leaf 1 again asks for the next leaf. And next leaf 2 asks for the next leaf. So now we are looking at these stacks because this is kind of where we left off in the pre-order traversal. So we're on node 5 over here. So that means we can pop this guy off of the stack. Is this a leaf? No, it's not. So we add its right and left child to the stack. So 8 and 7. Then we pop 7 off of the stack. We see that 7 is indeed a leaf. And so we immediately return it here to next leaf 1. So let me actually just make sure I erase this circle over 5. Otherwise, it will not be erased. Let me just add these items back to the stack. Okay, so now we have 8 on the stack. And sorry, I just popped off 7. And as I was saying, we returned 7 over here. So we're going to say next leaf 1 is equal to 7. All right, so now we have found the next leaf for tree 1. We just need to do it now for tree 2. So now at tree 2, we see that we left off at node 7. Node 7 is a leaf, and so we immediately return node 7 after popping it off of the stack. Now we see that the next leaf in the leaf traversal of both of these trees is 7, and so we kind of, tick some box or just say, all right, this is good, we can continue, let's look for the next leaf node. Okay, so now what we're going to do is the same thing. We're looking for the next leaf node in tree 1. Now we see that we left off at node 8. We pop node 8 off of the stack. We see that node 8 is a leaf node, and so we return 8 over here. Then from tree 2, we see that we were at node 3. So we look at node 3. We see that node 3 actually is not a leaf node, and so we need to add its children. It doesn't have a left child, so we just add the right child on the top of the stack, although first we did need to pop node 3 off. All right, so now we keep going here because we have not found the next leaf yet. So we're at node 5. We pop this off of the stack. It's not a leaf. And we add its 2 children to the stack. So we add 6, and then we add 8. And then we keep going because we have not found a leaf. So we pop 8 off of the stack. We see 8 is here. 8 is now a leaf. And so we immediately return 8 over here. So now this is equal to 8. These are the same, and so we continue. Now again, the reason that we're continuing here is because we have not finished traversing all of the nodes. Both of these stacks still have nodes on them, and so we continue. Now it's worth noting that if either of these stacks no longer has any nodes on them, then we are going to stop. So if, say, tree 2 has a node on it, but tree 1 does not, then we would immediately stop the algorithm and we would just return false, because what this means is that there is a node on tree 2 that's potentially going to lead to another leaf node, or is a leaf node. If there's any node here, this means that there must be another leaf node coming in the tree at some point if it's not this node itself. And well, we've already finished processing all of the nodes in the other tree because the pre-order traversal is done. And so that really just tells us that the leaf traversals cannot be the same because one tree has more leaves than the other tree does. So hopefully that's clear, but just remember that we are stopping as soon as either of these stacks does not have any elements in them. Okay, but anyways, we're going to continue here. And so now what we're looking for is the next leaf in tree 1 and tree 2. So we ended off at 3 at tree 1. So that was here. This is not a leaf. Pop it off, add its child, which is a 6. Then we look at 6, pop it off of the stack. We see that 6 is indeed a leaf, and so we return here. We write a 6. Now we're here at tree 2. We see 6, we pop it off, 6 is a leaf, so we return 6, and then we see that these are the same, and so we continue. Now when we come to the while loop condition, we see that both of these stacks do not have any nodes on them, and so we stop, and then what we do is we check if either of these stacks have any nodes on them. Now I know that seems contradictory to what I just said, but the thing is we stop running through this while loop as soon as either or both of these stacks do not have nodes on them. And so we don't know if we stopped because one of the stacks doesn't have nodes on them or because both of the stacks don't have nodes on them. And so we now need to check if both of the stacks are empty, because if both of the stacks are empty, that means that we are good. We actually did have the same leaf traversal, but if either of the stacks do have elements on them and the other one doesn't, as I was saying, that means there's going to be more leaf nodes in the traversal of one tree than the other, and so we would return false. So after we go through this process, we still need to check to make sure we didn't miss any leaf nodes. Anyways, I hope that's clear, but that is kind of solution 1. That's really all we do. This is saving us this space because, again, we don't need to store all of these nodes in the order in which we visit them. We just visit them one at a time and check one at a time to make sure that they are in the correct order. So as I said, this solution runs in big O of n plus m time, and this takes big O of h1 plus h2 space. Now the reason it takes this much space is because these stacks right here will never have more than the height of each binary tree elements on them. The reason for this, as you kind of saw when I was going through this, is that it takes at most h time to reach a base case in our kind of iteration here. Now, a base case is a situation where one of the nodes that we see is a leaf. So a leaf can only be situated at most at h height in the binary tree. And so to reach a leaf will only take at most h time. And so as soon as we reach a leaf, we're going to remove an element from the stack. And so our space will now be reduced from what would have been potentially a maximum of h to h minus 1. And then it could go back to h, but again, if we went back to h, that would mean that we are now at another leaf node. We would then remove that leaf node from the stack. And well, if you go through this example, you'll see that we will never have more than h elements on either of these stacks. Now, I can just quickly run you through to make sure that everyone's clear on why this works, but when we're doing the pre-order traversal on this tree here, you can see that we add element 1 onto the stack, then we pop it off, then we add element 3 and element 2 onto the stack, then we pop element 2 off. We then add element 4 and element 5 to the stack. So we have 5 and we have 4. We then pop off 4. This is a base case, right? We've just reached a situation where we're at a leaf, so there's no more nodes to add here. So then we pop off 5 right after we reach that base case. And then from 5, we need to add 8. We need to add 7. 7 is a base case. We remove it. 8 is a base case. We remove it. Now we're at 3. We pop it off and we add 6. Now, of course, this example does not necessarily prove exactly what I was saying, but hopefully it kind of solidifies or backs up what I was saying, that we're only going to have at most h elements on either of these stacks. Now, since we have 2 stacks, we'll have one stack that has h1 elements on it, the other stack that has at most h2 elements on it, and so we need to add this together to get a total space complexity of h1 plus h2. Now, the time complexity of n plus m is because a pre-order traversal takes n time for any binary tree. We of course have 2 binary trees, and so 2 pre-order traversals that we need to do. So that gives us the n plus m time. All right, so that is solution 1. Let me clean up the screen now, and then we'll move into solution 2, which works in a little bit of a different way. So I've just cleaned up the screen, and now we're going to move on to solution number 2. Now, the first thing I'll say about solution 2 is that it is much more complicated than solution 1. Now, it does run in a better space complexity. I may have made a mistake previously by saying that it runs in the same space complexity. That is not the case. This does run in a slightly better space complexity than solution 1, but it is much more complicated. So if you were in a coding interview, you would have to make your choice. Are you okay going for something that is not the most optimal solution, but that is going to be easier to implement and easier to code out? Or would you rather go for something that's more complicated, potentially more impressive, but that is more prone to you making a mistake or not being able to explain? So that's up to you and your comfort level with the solutions. Personally, I would go with solution 2 just because it is something that's going to be slightly more impressive. This is a very unique and creative solution, as you'll see as we go through it. But of course, if you feel like it may be too difficult to implement or you don't have the time to do so, it would be better to go with something like solution 1 because at least you can get that done and finish it in the time that you're allocated. Anyways, one thing to note about this solution is that the way we're actually going to save space here is not by processing one leaf node at a time, but instead it's by actually reusing the input to store the order in which we visit these leaf nodes. So what we're going to try to do is create a linked list of all of the leaf nodes that are connected in the order in which they are traversed in the pre-order traversal. Then what we want to do is get access to the head of these two linked lists and then look at these linked lists, kind of iterate through them at the same time and check the node values to make sure they match and that the lists are the same length. Of course, if these lists are identical, that means that the leaf traversal is the same and we return true. If we have any discrepancies or these lists do not have the same number of nodes or something, then that means that they are not the same and we would return false. So the way we'll create this linked list is by modifying the right attribute of all of these binary tree nodes, because this is a binary tree that has no children, and so we can use its .right attribute that currently is pointing to none to actually point to the next leaf node in the binary tree without kind of screwing up the binary tree and screwing up our traversal. So that is the idea here. So the question is, how do we do this? Well, first, I have to note that we're going to do this one at a time. So we're going to do the kind of connection and the creation of this linked list for tree 1, and then after that's done, we'll do it for tree 2. And so the process I'm going to show you here is relatively complicated. I'm just going to show you how to do it on tree 1, so I'll move tree 2 out of the way here. And then, of course, you could repeat that process for tree 2, and you would end up with the same kind of linked list and all of that. Anyways, let's go through it on tree 1. So I need to create 3 variables here: current, head, and previous. Now, the idea is once I find a leaf node, I need to try to connect it to the linked list, or I need to make that the head of my linked list if that's the first leaf node that I find. So node 4 here is very important. It's the leftmost leaf node, which means it's going to be the head of our linked list. And so we need to keep track of this node because this is how we're going to access all of the other elements and kind of go through what the leaf traversal actually is. So we need to know what the head node is when we do this. We also need to know what the current node is that we're looking at, and we need to know what the previous leaf node was that we had. The reason we need to know what the previous leaf node was is so that we can, again, use that to connect the next leaf node that we find to the linked list. So once we find 4, this is the head, this is also our previous node, and then we get to 7 and we say, okay, the previous node .right is equal to 7. 7 now becomes the previous node. We then find 8. 7 now connects to 8. 8 becomes the previous node. We find 6. 8 now connects to 6. 6 becomes the previous node, and then we see we don't have any more leaf nodes, and so we're done. But that's the idea here. So this is actually going to run recursively. We're not going to do this iteratively, and we're just going to run a pre-order traversal, but with a few different operations. So we're going to start at node 1, so current is equal to 1, and to start, the head is equal to none, and the previous node is equal to none because, well, when we start, we don't have a head and we don't have a previous node. So we start at node 1, and we look to the left and we look to the right. And actually, before we do that, we check if node 1 is a leaf node. Now, if node 1 is a leaf node, then what that means is we would set our head to be equal to node 1, because that's the first leaf node that we found. We would set the previous node, the previous leaf node to be equal to node 1, and then we would continue. Anyways, it's not a leaf node, and so all that means is we need to look to the left and we need to look to the right. So from node 1, we're going to recursively call the same function, which is going to try to create a linked list out of all of the leaf nodes rooted at node 2, and then all of the leaf nodes rooted at node 3. So really what will happen is when we call this function on node 2 and we call it on node 3, both of these will return to us the head node of their linked lists and then the previous node of their linked list as well. And this way we can then connect these two independent linked lists together. So to give you a better example, let's say we actually have another node here, 9 and 10. Well, when we recursively call on these two right here, what's going to happen is we're going to get this linked list, or we're going to have two unique linked lists. We're going to have this one and we're going to have this one. Now, the head of our second linked list is 9. The head of our first linked list is 4. So now we need to connect these two linked lists together. And the way we do that is by connecting the previous node, so the last node we visited or found that was a leaf node in kind of this left subtree, with the head of the right subtree. So hopefully that kind of makes sense, but that is the idea behind this. So let's get rid of that example. Now we'll go back to the original tree. Anyways, we look at node 2 and node 3. So now we go over to node 2. Now from node 2, we see this is not a leaf node, and so we need to look at node 4 and node 5. Now when we get to node 4, what we see is that this is a leaf node. And since this is a leaf node, we need to check if we should make this the head node of our linked list. Now, since this is the first leaf node that we found in kind of the recursive call over here to the left, that means that this needs to become the head node. And so we say the head is equal to node 4. This also means that this node needs to become the previous node. The reason it needs to become the previous node is because now this, as we continue on with the traversal, will be the previous node that we found that was a leaf node. And so that's what we have, 4 and 4. And I should have been changing current here, but I think you get the idea. Current is equal to 4. So now we're done with this, and so what we return is the head node and the previous node to this function called 2 right here. So now that we're at node 2, we need to look in this right subtree, and we need to try to connect these nodes together that are leaf nodes. And so from node 2, we call node 5. Except now when we call node 5, we are going to pass the head and the previous that we found from this left subtree call. Because since we look to the left first, we know that any of the nodes going to the right, well, they need to be connected to the head that we found to the left, right? Hopefully that kind of makes sense. But if we found a head on the left, so we found the first linked list leaf node in the left subtree, then this now needs to connect the next nodes that we find that are leaves in the right subtree. And so we pass the head and we pass the previous to the call to 5. So now the current node is 5. The head and the previous here are still equal to 4. And now from node 5, it's not a leaf node. And so we need to look to the left and we need to look to the right. So now we change our current node to be 7. We look to the left. This is a leaf node. So we don't need to change the head this time because we already have a head of our linked list. Instead, what we need to do is connect the previous node to the current node. So we say that the prev, standing for previous, dot right is equal to whatever the current node is, which in this case is 7. And so that kind of draws this connection right here. Let me draw it in a different color so that it stands out. So we've just made this connection now. We've connected node 4 and node 7. And so we can kind of erase this line. And now what we do is we set the previous node to be equal to the current node, which is 7, because now this is the last leaf node that we found in the traversal of this tree. And so now we're done with 7. So we go back up to 5. So current changes to 5. And now we look to the right. Now when we go to the right, what we do is we pass the head and we pass the previous node again, right? And so when we do this, we pass the head and we pass the previous. Now when we're on node 8, we see that this is a leaf node. And since this is a leaf node, we connect the current node, which is 8, to the previous node. So 7 connects to 8, so we kind of draw this line here. We then change the previous node to be equal to the current node, which is a leaf node. So now this is 8. And then we go back up to 5. Now that we're back up at 5, we see that 5 is done. We have kind of finished processing this node right here because we visited it, we look to the left and we look to the right. And so now the current would be 5. But now what 5 does is it returns the head and the previous that we found to node 2. So now we come to node 2. So the current node is equal to 2. And then from node 2, we're done. We've looked in the left subtree, we've looked in the right subtree, and so we go back up to node 1, and what we return is the head and the previous. That way, from node 1, when we try to connect the right subtree, we can pass the same head and the same previous. Anyways, now we're on node 1, so current changes to 1. So now from node 1, we look in the right subtree, we look at node 3 because we've already finished all of this. So we go to node 3, we see this is not a leaf node, so the current was 3, but since this is not a leaf node, we need to continue. There's no left child, so there's nothing to do there, so we just look to the right. So now that we're looking to the right, we see that our current node is equal to 6. This is a leaf node, and so what we now do is connect the previous node to this leaf node. So we draw this connection right here. We then change the previous node to be the current node, and the head stays the same this entire time. And now we see that we're done with node 6, so we go back up to node 3. We see that we're done with node 3, so let's change this to 3. So we go back up to node 1, so this changes to 1, and now we're done with node 1, and so what we return from here is again the head and the previous node. And so now the head and the previous node come to whatever called this, and so now we have access to node 4, and if we look at its right pointer, that gives us access to node 7. And then 7's right pointer gives us access to node 8. And then 8's right pointer gives us access to node 6. And this is the order in which these nodes are visited in the leaf traversal. And so now if we want to look at this leaf traversal, we just traverse through this linked list that we found. Now we do the exact same thing for tree 2. Now I won't walk through the process because we've already just went through this and it'll be really the exact same thing just with tree 2. When we go through tree 2, we will draw these connections right here. We will also have access to node 4. And so now what we'll do is we'll traverse through these linked lists at the same time. So we have kind of our 2 linked lists. We can just draw them out. So 4, 4, 7, 7, 8, and 6, and then 8, and then 6. And so now we just kind of have 2 iterator variables. So I, and maybe we make this one j, and then we just check if I and j are the same. If they are, we increment them. So I goes here, j goes here, check if they're the same. If they are, we increment them. So I goes here, j goes here, they're the same. So we increment them. I goes here, j goes here, they're the same. So we increment them. I and j are both equal to none. And now we know that these linked lists are the same, which means the leaf traversals are the same, and so we return true. But if we added like an extra element here, like maybe we add a 1 or something, then I would be equal to some value, but j would be equal to none. That would tell us there is more leaf nodes in this first tree than the second tree, and these leaf traversals are not the same, and so we would return false instead. So that is actually going to wrap up this solution. Now this solution runs again in big O of n plus m time and takes big O of h1 plus h2 space. The reason it takes h1 plus h2 space is because we need to run the pre-order traversal on both of these trees. And running it on these trees, as I showed you, will take h space, whether you're doing it iteratively or recursively, because you need to store all of the function calls that have not yet terminated on a recursive call stack. Now, as I showed you with the stack, it's the exact same thing here with a recursive call stack. You will only ever have at most h elements, where h is the height of the tree on that stack, before you reach a base case, and then you will reduce the space on the stack. And then you will maybe go to h again, you will reduce the space, go to h again, reduce the space, so on and so forth. You will never have more than h elements on that stack. And really, if you wanted to be super precise here, you could say that the space complexity is equal to the maximum of h1, h2. Now it's fine to write h1 plus h2 because we're doing an upper bound, and in terms of the analysis, this is fine, this is acceptable, but really it would be max h1, h2. Now the reason it's the maximum of h1, h2 is because we're doing these operations one at a time. So we're connecting these nodes in tree 1, and then once we finish doing that, we're connecting the nodes in tree 2. And so we use the maximum of either the height of the first tree or the height of the second tree, because once we finish doing the operation for one tree, then we move on to the second. So whichever one uses more space, that's the most amount of space we'll ever have used at any point in time. Now again, it's still accurate to write h1 plus h2 because this is an upper bound. This still works. This is still correct for big O notation. But if you wanted to be more precise and get closer to what it actually is, you would write the maximum of h1 comma h2. So anyways, with that said, that is going to wrap up this conceptual overview. Now let's implement these solutions in the code walkthrough. So I'm here in my code editor, and I have my compare leaf traversal function defined, which has 2 input parameters, one called tree1, the second called tree2. Now I'm going to begin by defining the stacks that we're going to use to actually traverse through both of these trees. So sorry, I will start with solution 1, and then I will move on to solution 2 because we do have 2 solutions to implement here. So I'm going to say tree1, and then traversal stack is equal to a stack that has tree1 on it, so the root node. And I'm going to say tree2, traversal stack is equal to, and then tree2. And then I'm going to say, while the len of tree1 traversal stack is greater than 0, and the len of tree2 traversal stack is greater than 0. So while both of these stacks have nodes on them, then we are okay to continue this loop. So the first thing I'm going to say here is tree1 leaf is equal to, and this is going to be a function, get next leaf node. This will take the tree 1 traversal stack in. And then similarly, tree 2 leaf is equal to get next leaf. And this will be tree 2 traversal stack. All right, so as I was saying in the conceptual overview, this is where we will call this function that will perform kind of part of the pre-order traversal. It will then return to us the next leaf node that it finds. So now that we have both of the leaf nodes, we'll say if tree 1 leaf dot value does not equal tree 2 leaf dot value, then we can return, and we will return false. All right, and that will actually conclude this first function right here. We do have to code out some more, but then after this, what I'm going to do is I'm going to say return the len of tree 1 traversal stack is equal to 0, and the len of tree 2 traversal stack is equal to 0. So the reason we're doing this is to ensure that both of these stacks are empty at the end of this traversal, because if either of these stacks have any elements on them, that means we have not yet considered all of the leaf nodes, and well, these leaf traversals are not the same. So now what we need to do is code out the get next leaf function. So we're going to say define get next leaf node. This is going to take in a traversal stack, and then what we're going to do inside of here is say that the current node is equal to, so current node is equal to, and then traversal stack dot pop. Now what this will do is take the top node off of the traversal stack. We know that we have at least one node in this stack, because if we didn't, we wouldn't have called this, because the while loop would not have actually gone into this iteration. All right, and now we're going to say while not, and then is leaf node, and we're going to pass the current node, and this is a function that we'll define in 1 second, and what this function will tell us is if the current node is a leaf node. So we're going to say define is leaf node, and this is going to take in a node, and we're going to return if the node dot left is none and the node dot right is none. So if both of the children are none, then this is a leaf, and well, we will return true. All right, so now that we know if this is a leaf or not, if it is not a leaf, what we need to do is continue this traversal and look for a leaf node. So we're going to say if the current node dot right, so if it does have a right child, so if this is not none, then we will add to the traversal stack, so not return, but add to the traversal stack this right child. So traversal stack dot and then append, because we're treating the end of the array like the top of the stack, and we'll add the current node dot right. And again, the reason we're adding this first before the left node is because on a stack, whatever you add last comes off first, and we want the left node to come off first, so we'll add that second. So we'll say if the current node dot left is not none, and then similarly, we will say that the traversal stack dot append, and then this will be the current node dot left. Okay, and then finally, at the end of this iteration here, we're going to say that the current node is equal to, and then traversal stack dot pop. So we're popping off that next node, setting that equal to the current node. So then when we continue this while loop iteration here, we can check if this new current node is a leaf node or not. And then finally, what we're going to do here is we're going to return the current node, because as soon as the current node is a leaf node, we will not enter this while loop. We will return that leaf node, and then we will continue running from inside of here. So that actually concludes this entire algorithm. So as a reminder, this solution runs in big O of n plus m time. And this takes big O of h1 plus h2 space, where n is the number of nodes in the first tree, h1 is the height of the first tree, m is the number of nodes in the second tree, and h2 is the height of the second tree. Now let's just quickly run through this to make sure it's clear. So we define both of our stacks for the iterative pre-order traversal. We say while the len of tree 1 traversal stack is greater than 0 and tree 2 traversal stack is greater than 0. So while both of these stacks have nodes that need to be visited and processed, what we will do is look for the next leaf node in both tree 1 and in tree 2. And then we will check if those leaf nodes have the same value. If they do have the same value, we continue. Otherwise, we return false. This means that the leaf traversals are not the same. Finally, at the very end of all of these iterations here, we check if either of the stacks have elements on them. If they do not, that means that the leaf traversal was the same, and so we return true. All right, so going into get next leaf node, we take a traversal stack. So either the tree1 traversal stack or tree2 traversal stack, we say the current node is equal to the element on the top of the stack. And then we check to see if this node is a leaf. If this node is not a leaf, what we do is add the right child and the left child to the stack in that order. And then what we do is we say current node is equal to traversal stack.pop. So we take whatever the top node is now, which should be the left node if we have a left child, make that the current node. We check if this new node is a leaf node. If it's not, we repeat the process until eventually we find a leaf node, and then we return it. Of course, this isLeaf function is straightforward, just tells us if a node is a leaf. So that is solution 1. I'm going to comment this out. I'm actually going to copy this isLeaf function because we'll reuse this. So let me just paste this down here. And now we'll move on to solution 2. So let me actually copy this function signature as well because we will reuse this. Okay, so define compare leaf traversal, tree1, tree2. Now for solution 2, things are going to be a little bit different. We're going to start by saying tree1, and then this will be leaf nodes linked list is equal to, and then this will be the connect leaf nodes function that takes in tree1. And sorry, this needs to be comma underscore. I'll describe why we need that in 1 second, but essentially this function returns to us 2 values. We only care about the first value, which will be the head node of our linked list that's created from the binary tree nodes. I'm going to copy this and say tree2 leaf nodes linked list is equal to connect leaf nodes tree2. Now, before I actually finish coding out this function, let's just write out connect leaf nodes because this is where most of the logic is. I'm going to say define connect leaf nodes. I'm going to take in a current node. I'm going to take in a head, which is tentatively equal to none. And then I'm going to take in a previous node, which again, by default is set equal to none. Okay, I'm going to check if the current node is none. So if the current node is none, this is kind of a base case. What I will do is return the head node and the previous node. That's what we're always returning from this function is the head node and the previous node. So in the situation where the current node is none, we just return whatever the head and previous node was from the last call. All right, we now say if is leaf node current node. So if the current node is a leaf node, we need to connect it to the linked list. So we say if the previous node is none, which means we have not already found a head for our linked list. In other words, this is the first leaf node that we found. Then what we say is head is equal to current node. Otherwise, so if there is actually a previous node, that means that we already have a head. And so we can say that previous node dot right is equal to the current node to connect this to the linked list. Okay, so now we will come down here and we will say previous node is equal to current node. We do this regardless of what happens because the current node is a leaf node, which is also the last leaf node that we found as we move on to the next iteration. And that allows us to then connect the next leaf node to it, right? Because we say previous node dot right, we're changing that right attribute to be equal to the next leaf node that we find. Okay, then what we're going to do down here is we're going to recursively call this on the left and the right subtree. So what we need to do is say that the left head and then comma, the left previous node is equal to, and then connect leaf nodes. We're going to pass in the current node dot left, whatever the head is right now, and whatever the previous node is. And then we're actually going to return connect leaf nodes. This time we're going to call on the right subtree, so current node dot right, but we're going to pass what the left head was and what the left previous node was. So this part here is probably the most confusing, but what this is doing is looking in the left subtree, and then it's getting whatever the left head and the left previous node is. So all of these function calls return to us the head and the previous node, right? Because this is kind of our base case. So as soon as we hit the fact that current node is equal to none, whatever the head is and whatever the previous node is returned. So this function always returns to us 2 values. And so we capture these 2 values, and the point of capturing these 2 values is to use them in the call to the right subtree. So the left subtree will hopefully give us the head of our first leaf node. Then we will also get the previous node, so the last node that was a leaf node that we found in the left subtree, which could be equal to the head, but oftentimes will not be equal to the head. So now we know kind of the beginning of our linked list and the very end of our linked list. So then we pass those pieces of information now to the call to the right subtree so we can connect the left linked list with the right linked list. So if we pass the left head, we can now store this through all of the function calls here, all of the recursive calls. So eventually when we return back here, we get the head of our linked list. And then we have left previous node. Again, this allows us to actually connect the last leaf node that we found to the next leaf node that we find in the right subtree. So that's the idea behind these two lines. Now, we're not quite done here, but at this point, what we should have if these two functions have executed is the head node of both of the linked lists for all of the leaf nodes for tree 1 and for tree 2. So again, this will just be a binary tree node. You can see up here we have our binary tree class, and we'll use this right attribute here to kind of access the next element in this maybe imaginary linked list. So now what I want to do is I want to compare these two linked lists together and see if they have the same nodes. So I'm going to say list, this should be list 1 current node is equal to, and then this will be tree 1 leaf nodes linked list. I'm just writing this out so it's a little bit easier to read. I'm going to say list 2 current node is equal to tree 2 leaf nodes linked list. And then I'm going to loop through both of these linked lists. So I'm going to say while list 1 current node is not none and list 2 current node is not none. And then I'm going to check if these nodes have the same value. So if list 1 current node dot value does not equal list 2 current node dot value, then we're just going to immediately return false. Otherwise, we're going to move to the next element in these linked lists at the same time. So list 1 current node is equal to list 1 current node dot right. And I'm going to say list 2 current node is equal to list 2 current node dot right. And then I'm going to return list 1 current node is none and list 2 current node is none. So let me walk through this. What we're doing is setting up these two variables as kind of our iterator variables for our linked list. We're looping until one of these linked list nodes is equal to none. As soon as one of them or both of them are equal to none, then we stop this loop and then we check if both of them are equal to none. So if both of them are equal to none, that means that we can return true. The reason we can return true is because these linked lists or these trees specifically had the same tree traversal. And we know that because if they didn't, we would have returned false. And now there's no more leaf nodes that we need to consider. And so we go ahead and we return true. But if one of these linked lists still has nodes in it, there's extra leaf nodes in that linked list. And so we just return false. Anyways, if that's not the case, so if we haven't exited this while loop, then what happens is we just compare the current value of both of the nodes that we're looking at. If these values are not the same, we immediately return false. If they are the same, we keep looping and then check the next values. So anyways, as a reminder, this solution runs in big O of n plus m times, so the same time complexity as previously, but takes big O of, and then the max of h1, h2 space, due to the fact that both of these operations happen sequentially. So this one happens first, uses h1 space, then this one happens second, the h1 space is now gone, and now this uses h2 space. And so whatever the maximum of these two spaces are, that's what we will have as the total space complexity of this solution. So anyways, with that said, that is going to conclude this code walkthrough and this video. I hope this was helpful to you, and I look forward to seeing you in another AlgoExpert question.